Hello, and welcome to our webcast on General Principles of Proficiency Testing for Analysts. The topic of this webinar is based around the expertise of Fera science in the proper implementation of a wide range of proficiency testing services. The global market for food testing services is projected to undergo enormous growth in the next few years, accompanied by increasing regulation of food standards. In addition, consumer awareness of food safety, authenticity, and the effects on health is also driving this demand. These demands must be met by accurate, robust, and reproducible testing methods. In this webinar, we will cover several topics, including the testing processes themselves and the importance of using blanks and reference materials, considerations of sample stability, particularly if samples have been in transit or in storage for some time, results of testing, the appropriate analysis and interpretation of those results, and good practice for recording test methods and data, and quality control and reproducibility. To discuss these topics, it's my pleasure to introduce Mark Sykes. Mark has been a senior scientist at Fera for over 20 years and is the scientific advisor for proficiency testing, responsible for overseeing the scientific integrity of all proficiency testing services. Mark's background and expertise is in analytical chemistry, in particular mass spectrometry, and his expertise includes techniques that are essential for robust food testing procedures. Mark has an extensive record of peer-reviewed science and is active in the scientific community, publishing his work on proficiency testing data and speaking at international conferences and workshops. He is also the Fapas representative for the UK Proficiency Testing Working Group. So I'd like to hand over to Mark and hope you find his discussion interesting and informative.
Thank you very much for that introduction. This presentation came about because a lot of our customers want some help in interpreting the outcome of a proficiency test and want some understanding in the principles of proficiency testing, how it works and what it means for them. So this presentation is aimed at that audience. Okay, so relevant questions to ask that we're going to address is: how does proficiency testing work? What happens when it goes right? Equally important, what happens when it goes wrong? And overall, what can we learn from this? This presentation is split up into bite-sized sections so that you can dip in and out as you wish or go directly to the topic of interest. And the topics are listed here on this slide and they will be in this order. So we start with section 1, which is the general PT process. What is proficiency testing? How do we describe this to someone who is not familiar with it? If I ask you to do a routine analysis, so I'm a customer of your laboratory, how do I know that you're giving me the correct answer? Ultimately, this is what it's about. So, as a laboratory, we might have a validated method. We might have some kind of internal quality control mechanism. We might have accreditation, typically to an international standard, ISO 17025. And these are all good and proper things to have. But what they have in common is that they are largely internal control mechanisms. That is to say, the control is within the scope of the laboratory and there is no external influence. And that is where proficiency testing comes in. It can help give you a measure of the bias against an external reference that is one that the laboratory has no control over. The overall process starts with test material preparation, which might include natural levels or spiked samples. The PT provider then has to carry out a homogeneity test. So this is to establish that all the samples that each participant receives is all the same. And typically we would do this by taking 10 samples at random and analysing them in duplicate. And we would use a laboratory to do this for us, which typically would use an ISO 17025 accredited method. Then it's the turn of the participants to receive their sample, carry out their analysis and report the result. Once we have all the results in, we do a data assessment. That is quite involved. It involves statistical assessment, but the outcome is the Z-score, which participants are familiar with. And this is all produced in a report. At any one point in this process, we can learn from the experience and improve the PT for next time. This process is also described in the International Harmonised Protocol for the Proficiency Testing of Analytical Chemistry Laboratories and is also described in ISO 17043, which is the standard general principles for proficiency testing providers. So, the test material itself, this is important to get right, and it could be liquid or it could be solid. If it's a liquid, is it an oily liquid or is it aqueous? What about stability? The matrix itself could be unstable or the analytes could be unstable. What about compounds that bind to the matrix? Are there physical chemical parameters related to that material? How are we going to store it or transport it? What kind of containers should we use? Metals, for example, we need to avoid glass containers because they would contaminate the sample. Are we looking at incurred or natural analytes, or do we have to spike in the analytes artificially? What about test materials that are unintentionally contaminated, for example, with genetically modified organisms or allergens? These are questions that the PT provider needs to address. But importantly, as a participant in a PT, how do I know that my test material sample is the same as your test material sample or anyone else's taking part in this PT? As part of the PT process, I mentioned the homogeneity testing. So what does this look like in practice? These are typical homogeneity plots that may or may not occur. So plot number 1 is really what we're aiming for. These are the 10 samples analysed in duplicate, so you can see a blue cross and a red cross associated with each sample. This gives us a measure of both the analytical variance in that homogeneity test as well as the sample to sample variance. Plot number 2 shows that the sample to sample variance is not too bad, but sample number 2, the duplicates, are far apart. the Red Cross and the Blue Cross are very different. This indicates a possible analytical error during the homogeneity analysis, and we can account for this in the statistics. Plot number 3 shows sample number 9, where both the analyses, the Blue Cross and the Red Cross, are very different to the other samples. This indicates a lack of homogeneity for that one sample. Plot number 4 is a more extreme version of plot number 3, where it's showing clearly that the sample is not homogeneous. There is a statistical process underlying this analysis, which is too far-reaching to go into detail in this presentation, but these plots are the outcome and the type of thing we're looking for as a PT provider. And then finally, in the process, it's the analysis of the sample by the participant. So we help the participants as much as we can. We provide a deadline and online reporting for the results. But please follow the instructions on the letter that accompanies the test material or that is available online associated with that sample. The instructions are there to help you, but sometimes there might be critical parameters in those instructions to be followed. Usually you will use your own routine method. There should be nothing special or challenging about a PT. It should be normal. Sometimes we might ask for critical method parameters and information regarding those parameters to be returned with your results. Further method details. This is an optional part of the proficiency test, but we do encourage participants to submit method details so that we can capture these and look for trend or analyse for trends with methods against results. This is very useful information both for us as a PT provider and for other participants in the proficiency test. But overall, the PT should be fit for purpose. Section 2. Sample stability. So, Fapas is a truly international PT provider. We ship out our samples from our office in the UK to many countries around the world. Some of these countries are in the Far East or South America, and it can take several days for the samples to reach their destinations, even when sent by courier. So a valid question to ask is, are these samples stable for the duration of that transport? One specific question was asked to me recently by a laboratory in a Far Eastern country, and this was about veterinary drugs, in particular beta-lactams, in bovine milk. And in order to answer this question of stability, I looked at the data, and what we see on this slide are all the Z-scores from laboratories taking part that are a long distance from the UK. That is, the samples had to travel a long way. The countries and the territories that they went to are listed there, so they include China, Hong Kong, Taiwan, Costa Rica, India, Singapore, Thailand, and the USA. If there was a sample stability issue we would see a trend in the data. That is, the results from all of these labs would be compromised in some way. But when we look at the data, actually the majority of them achieve good Z-scores, around about 0. There are one or two extreme Z-scores, but there is no trend. And if we look at the histogram for cloxacillin in this example, we see it is symmetrical and normally distributed. There is no evidence of instability for this sample. We can also do formal stability testing. This example is a canned meat test material for hydroxyproline, and we can do a stability test over a period of weeks, and this is the data that we might get from such an experiment. The samples are put at regular intervals into extreme conditions and then analysed against a sample that is stored at ideal conditions. And we can plot a graph, as we see here, which shows a slight downward trend indicating potential instability. But if we look at the half-life of this graph, we can see it's estimated at 123 weeks. That means it would take about 2.5 years before the level of hydroxyproline in this sample got to half of its level if it was stored at 35 degrees C. Clearly that's not going to happen, that's too extreme, so under normal storage conditions this is perfectly stable. We can also do very specific stability testing. Vitamins in particular might be compromised by stability. A few years ago we introduced our first vitamin C proficiency test in a fruit puree. In order to minimise the possible instability, we had a short time scale and a courier dispatch for this sample, even for countries close to the UK. We shipped the samples in insulated boxes, and we did an experiment where we had samples in an insulated box at 4 degrees C compared to the ideal storage conditions of -20. And we can see that over the period of time for transportation, so nearly 2 weeks, there was no evidence of instability at all. For our food microbiology samples, we actually stability test all of these samples over the course of the PT, which is a 4-week period. And again, we have all the data to show there is no problem with microbiology samples. Another specific example was for dithiocarbamates. These are very unstable pesticides, and in fact its analysis exploits that because it measures the release of carbon disulfide as the dithiocarbamates break down. A typical example would be thiram. Again, before we released our first proficiency test on this, we carried out a levelling stability exercise. So you can see on this chart the difference in concentrations between samples stored at ambient conditions and those stored at 4 degrees C. There was an immediate drop in concentration over the first 1 day, that is 24 hours, but after that it clearly had stabilised over a 4-day period, which would be the normal period of time for shipment of those samples. So overall we have high confidence in the stability of our samples, either through evidence of the proficiency test or through evidence of formal stability testing for particular cases. Section 3. Results and method submission. So this is about how participants can enter results and their methods and the changes and improvements we've recently made to Fapas website reporting. So when you first log in to the secure pages, you will see a number of options under My Account. You can look at the orders, so the proficiency test that you've registered for. You can go to the results page to submit results. There's a reporting tab where all the reports are available, even historic ones that you've registered for, and there is a charting facility. More about the charting later. On the results page, you can see on the right hand image here a couple of examples. These are the two proficiency tests that this particular participant is registered for. So you can see that there is the option to submit results here. There is a number of options here for you. So there is a section on filtering, so you can filter by the company or the individual user of the website. So we recognize that companies will have several people who might want to access the secure pages. You can see results pages for PTs which are open or closed or have not yet started. You can also filter against the proficiency test or the matrix or the analyte. This gives you complete options for how you view your results entry. You can also see at the bottom of the page the product code associated with that PT and the PT number. On the right hand side, you can submit results or edit or add to results. So the submit results button is for a proficiency test where you have not yet submitted any results. You might have a proficiency test where results have been submitted but you want to edit them or add to them, and that is the difference between those two buttons. There is an additional complexity with a semi-blind proficiency test. This is one that combines detection and quantification. So typically this might be allergens or pesticide residues, veterinary drug residues, or even some of our newer multi-mycotoxins PTs or the PAHs. So this is where there is a list of analytes that you might have tested for, or perhaps they're not within the scope of your analysis and you might not have detected them. So here we have a default selection of not detected. This means that you have looked for that analyte but you have not found it. Alternatively, you can select not tested. This means that the analyte is not part of your routine analysis suite, so you would not be expected to look for it. And finally, you might have detected that analyte and you want to provide a result for it, in which case select Provide Result, and that will allow you to enter a quantitative result for that analyte. In addition to submitting one result, you might want to submit several results, and you might want to understand what is the difference between the results that you've submitted. Therefore, at the top of this page, your reference for these results. This is how do you want to remember this result? What does it mean to you? Is it for a particular analyst or technician in your lab? Is it for a particular method? That's up to you how you want to identify it. On the left hand side, the submission notes are the instructions that are copied from the instruction letter. So therefore it's important information about how to submit the results and in what format, in particular the analytes and the use of a decimal full stop. And finally at the bottom, the button Submit Results, that will be the last thing you click on to finally submit that set of results. Once you've submitted those results, it takes you to method submission. This will be any number of questions about methods that are specific to that proficiency test. You could skip this, it's optional, but completing the methods will help us to help you. So we do encourage you to do this. And in the final results summary, if you have a laboratory number which is circled there on the left hand image, that means that the submission was successful. So you've been given a laboratory number for that PT. On the right hand side, this shows where you might have multiple results submitted for that PT. We ask that one of those results submitted is representative of the laboratory result as a whole, and therefore that gives you the laboratory number for taking part. Other results submitted will not appear in the final PT report, but will appear when you log in to the secure pages. And that is indicated by the text. These results will not appear in the report. You have an options button where you can add, edit or change the result, so you can change which result you want to be as representative of the laboratory. A new facility also allows you to export your results in a CSV format, that is comma separated variables. This then can be imported into any standard spreadsheet program. This is a new facility that many of our participants have requested, and we're very pleased to make it available. Section 4. Use of blank materials. This is important, and in particular for analyses which use mass spectrometry. So typically in the past these have been for veterinary drug residues or for pesticide residues. However, it's being used more for other analyses, including mycotoxins, which historically have used conventional HPLC techniques. Why should we be concerned about matrix effects in mass spectrometry? This graph indicates what can happen in a mass spectrometer. If we're producing a calibration line, we aim to have a series of standards at different concentrations that are giving a linear response to those concentrations and going through the origin, that is the 0 point of that graph. So the solid line that is blue in the middle indicates no matrix effect. But with modern mass spectrometry, they are becoming much more sensitive instruments, and they are required to analyse for many compounds at once. So the extracts tend to be dirty, so not much in the way of cleanup. So there's a lot of matrix left in the sample extract as it goes on the instrument. This can create an effect, and sometimes it can enhance the response, so an enhanced effect, the green dashed line, or it might cause a suppression in the signal, and that is the orange long dashed line. So this will have an effect on your ability to accurately calibrate that instrument. This is the problem. How do we overcome that problem? There are several options. Stable isotope labelled analogues. Unfortunately, these are expensive, and if you're analysing 300 or 400 pesticides, are you going to have a stable isotope analogue for each pesticide? Are they available? Can you afford to buy such analogues? It's maybe not economically possible. What about a specific cleanup to reduce the matrix effects? This takes time, it takes expertise, and you might have losses because it adds additional steps in the process. And it might be too specific. If we're looking at multi-analyte analyses, then we might compromise the analysis of some compounds. So what about a matrix match calibration? You need an exact matched blank matrix to do this. So fortunately, Fapas blank samples are available, and these are prepared from exactly the same material as the test sample. So when we prepare a material, we have a bulk of blank material which we divide in two, partly for blank samples, partly for the spiked test sample. This includes all our pesticide residue matrices, some of our vet drug residue matrices, and coming soon by customer request, honey and matrices specifically for mycotoxins analysis. If you use the search term blank on our website fapas.com, you will bring up a list of all the current blank samples that are available. Section 5. The quality of the data analysis. This is about Fapas as a proficiency testing provider and what we do to ensure that you get the best assessment of your data possible. The assessment you receive is in the form of a Z-score. This includes the participant's result, the assigned value, and the statistic sigma p, which is the standard deviation for proficiency. This section of the webinar looks at how we derive the assigned value and how we derive the standard deviation. First of all, we need to decide which of the results we include in the assessment of the assigned value. In other words, which values are valid for the calculation and which are not valid and excluded from that calculation. All results will still get a Z-score, but not all will be included in the calculation. In this example, we've excluded 4 of the results. The result at the top, 1.432, is clearly not part of the population. The assigned value is 1404, so this result is clearly not in the same order of magnitude as all the others. The next 3 results have also been excluded, even though at least 2 of them are not very different from the assigned value. Why is this? Part of the instructions is that we require in this analysis, acrylamide, for results to be corrected for batch recovery. For these 3 results, participants stated that they were not corrected for recovery. Therefore, they are not valid for the purposes of our calculation. You will see in our reports and protocol that we refer to robust statistics, in particular the robust mean. What does this mean? If we have a set of data represented by this graph and the blue bars on the graph, we could calculate a simple mean value, but we see to the right hand side there are some outlying data points. We could use exclusion criteria, some kind of outlier test, but the thinking in the statistics is that it's preferred to use a robust method instead. And so we use a robust algorithm that reduces the effect of those outlying data points. In practice, this means that an arithmetic or simple mean is affected by the outliers. In this case, it gives a value of 8.11, but a robust mean gives a more correct or accurate value of consensus, which is representative of the majority of participants, and in this case it's different at 7.82. We might also get multiple populations of results. We use an adaptive kernel density estimation to find out if we have a multimodal distribution. Informally, this is called bump hunting because we're looking for bumps in the distribution. These may be error related or they might be method related, and it's important to try and establish what is the cause of this so that we choose the correct mode in the dataset. The standard deviation for proficiency must be objective and it must be prescriptive. This means we must know before the PT what is going to be acceptable for the analysis in question. It's not the same as the observed standard deviation of the data. That's a different kind of standard deviation. Where do we get these values from? Well, we might use predictive models, values from inter-laboratory reproducibility, typically collaborative trials, or we might use expert judgment where none of these are suitable. They might be defined in legislation. The Horvitz equation is used for the majority of contaminant analyses in food chemistry. This is the original Horvitz equation, and if you describe this as a graph, you get the Horvitz curve. It's a remarkable equation and it works for most analyses at most concentrations most of the time. So you will see this commonly used in Fapas reports. However, the original Hurwitz equation begins to fail at very low concentrations and at very high concentrations. At low concentrations, this is less than about 120 parts per billion, what we observe is that the Hurwitz equation is not appropriate, and in fact reproducibility levels off at about 22%, which is the red horizontal line on this graph. This effect was described by Professor Michael Thompson, the author of, or co-author of the International Harmonised Protocol for Proficiency Testing. There is a similar effect at high concentrations, more than about 13.8%, so this might be sugar in high sugar products, for example, where a further modification of the Hurwitz equation was also described by Thompson, and the graph is quite different. Does the Hurwitz equation still work? The original Hurwitz equation is nearly 40 years old, so is it appropriate to use it? Work by Professor Thompson and colleagues at Fapas produced this graph, where the coloured lines are the actual Fapas data from 2009, 2010 and 2011. The original Hurwitz function is described by the curved dashed line, and the horizontal dotted line is the Thompson modification. The fit of the observed data to theoretical data is remarkable. So yes, the Hurwitz equation does still work. We assume that distributions are normal. However, there are evidence of non-normal distributions. Microbiological results have long been known to be not normally distributed. They're often described as a Poisson distribution. So we can modify our statistical approach to compensate. Similarly, GM analyses are also non-normally distributed, and we apply the same correction as for food microbiology. The correction is to log transform the raw data. So you will see in our reports the z-score equation is modified with log 10 values instead of absolute values. In water microbiology, the transformation is not a log transformation but square roots, and this derives from work that Fapas has done on its own microbiology PT data. Section 6. Interpretation of assessments. So this is about receiving your z-scores, what they mean, and importantly, what should you do with them in the long term. In a Fapas report, you will see the results and the z-scores tabulated against the laboratory number. In a Fapas report, we highlight in bold font those z-scores which are outside plus or minus 2. We also provide a histogram of the z-scores to show what the distribution is compared to the other laboratories taking part and compared to the performance limits of plus or minus 2 z-scores. It's important to understand what this means. In particular, what happens when you get a z-score outside of plus or minus 2. And this is important in terms of the general trend of performance. There is an underlying assumption that we have a normal distribution. In fact, we can prove that we have a normal distribution in the data. There are statistical tools to do that. But what it means in practice is that within 2 standard deviations of a mean value, the area under a normal distribution is about 95%. Another way of looking at this is that the area outside of 2 standard deviations is about a total of 5%, 2.5% either side. So there is a 5% probability, or a 1 in 20 chance, that your z-score is outside of 2 even if everything is working normally. This is an effect of the statistical distribution. The probability of a z-score being outside 3 standard deviations, however, is a much smaller proportion of that curve. It's about 1 in 300. The probability, therefore, is not very good that you have a genuine result that is okay, but it gives you a z-score outside of 3. Therefore, that should be an action limit to investigate what has gone wrong. A z-score between 2 and 3 might indicate a problem, or it might simply be that 1 in 20 chance that everything is working okay, and it just happens to fall at the edge of the normal distribution. The distribution is a curve, not a step change. So this is an important concept. For some of our proficiency tests that are semi-blind, that are detection as well as quantitation, you might see a z-score of about minus 4.5, and in fact you might see a group of z-scores in that same region. This is highlighted in a vet drug PT distribution amoxicillin. Why would we have these z-scores of minus 4.5? One of the questions that we ask is about the limit of detection or quantitation, and in vet drugs, for EU regulatory purposes, this is the CC beta value. Not all labs will have a CC beta, so we also accept LOQ values. The assigned value in this case is 7.71, with a standard deviation of 1.6962. What we're doing is assessing laboratories on whether they should have been able to detect amoxicillin based on their CC beta. There is a mechanism for doing this, so we set a lower limit dependent on the assigned value and the 3 times standard deviation. So 3 times sigma p is 5.0886. Therefore, our lower limit, our criterion for assessing labs on their detection capability, is the assigned value minus 3 times sigma p, which is 2.62. If a lab's CC beta is more than this critical value, then we say that it's less than the CC beta. We give them the benefit of the doubt that they would not be able to detect that analyte. However, if their CC beta is below the critical value, they should have detected the compound, in which case we give them a result of 0, which equates to a z-score of minus 4.5. We also encourage participants to generate control charts. This can be done quite simply internally within the laboratory, and the advantage is that it gives you a measure of performance over a long period of time. One proficiency test is an idea of that performance on that one day on that one test material. It doesn't indicate what is the long-term performance of that lab. So a few data points in the top left chart here doesn't really tell us whether there's a positive bias or a negative bias. But by the time we've got about 100 data points, 100 z-scores for similar PTs, we can see that actually overall the trend is around about a z-score of 0. In other words, there is no problem with the performance in general. We make this easy for you. On the secure pages on your login, there is a button called Charts. You can use this to filter all your historic results for about the last 10 or 14 years, depending on how long you've been taking part, and it will produce a chart online for your purposes. We are in the process of updating this charting facility, so you will be able to filter it for different analytes or analyte groups, and it will highlight what different results mean in terms of multiple result submission. This is an enhanced feature that we will be launching very soon in 2018. Section 7. Method dependency and proficiency testing. Most proficiency tests, not just Fapas proficiency tests, do not dictate what method you should use. This should be your normal, routine method with no special treatment. Sometimes there will be method dependency, and we will describe this in instructions. We can also investigate method dependency in PT data. So some examples here. Is there a method dependency? Yes. So total fat hydrolysis. In order to measure total fat, you have to do a hydrolysis step. This could be an acid hydrolysis or an alkaline hydrolysis, and which one will depend on the matrix. Vitamins and allergens are well known for being method dependent. We can also investigate PT data to look for perceived method dependency, and sometimes we find there is no method dependency. Examples are hydroxymethylfurfural or HMF in honey, sodium in just about everything, and PAHs. For evidence and publications on all of these method dependencies, this list of publications on this slide is some of the scientific output from Fapas. Let's look at a couple of these examples in detail, starting with vitamin B2. In a liquid supplement, vitamin B2 cannot be its riboflavin compound. It has to be modified to be more soluble and therefore it's present as riboflavin 5-phosphate. This in turn creates an issue for its analysis, because riboflavin requires only an acid hydrolysis step, whereas the riboflavin phosphate requires an additional enzymatic digestion step which follows the acid hydrolysis. So two-step process. We see the outcome of that in the PT data, which is bimodal. So the left-hand mode corresponds to participants that have used only the acid hydrolysis. The right-hand mode corresponds to participants that have correctly used the enzymatic hydrolysis as well as the acid hydrolysis. We can look at the trend of this over time, and in fact we published this observation 7 years ago in the journal Analytical and Bioanalytical Chemistry. If we look at the trend of the charts from left to right, we can see that over the years and successive proficiency tests, participants have learned from the outcome of these PTs. So by the time we get to PT 2164, more participants are using the correct double process for the method than participants only using the simple method. And in fact, more recent PTs show a unimodal distribution where all participants are now correctly using the complete method. Allergens is well documented in the scientific press. You can see the effects on proficiency testing in that we need to separate allergens results according to the ELISA kit that labs use. And in fact, not just that, there might also be differences between the manufacturer's different ELISA kit products. As we can see here for gluten, where we have 3 assigned values, 2 of which correspond to the same manufacturer but different products. Not only can they give different assigned values, they can give very different distributions, as you can see in the charts below. For pesticide residues, there is a different effect. It's not analytical, but it is to do with the matrix effect of the sample. We prepare the material by taking a bulk matrix, screening it, spiking with pesticides, and then leaving it to stabilise, especially for cereal products. We then remix it and aliquot it out into PT samples. We know what the spiking value is, we know what the homogeneity value is, and we know what the assigned value is based on the consensus of participants. But what we observe is a remarkable difference between what we've spiked in and what we have as the assigned value. The chart at the top is a homogeneity mean value plotted against the consensus assigned value, and there's good agreement. However, the bottom plot shows that the spike value, that is the theoretical value that we've put into the material, is more than the assigned value, and in fact it's consistent to about a factor of 1.22. Therefore, we strongly encourage participants to interpret their performance based on the assigned value that we as the proficiency test provide, and not on the spike values or the homogeneity mean values. Section 8. This is about after the proficiency test and the uses of samples that remain. So this is about the difference between a QC sample, a reference material, or indeed a certified reference material. For many of our products, we've made available the samples after the proficiency test for quality control purposes. It enables laboratories to troubleshoot performance or simply to use it as an ongoing mechanism for quality control outside of the formal PT process. The data for QCs are derived directly from the proficiency test. We advise on the stability, but the stability is not formally tested, and we do not provide measurement uncertainty. It's just the PT data for that sample. A reference material is different. In the case of a reference material, we're using some of the proficiency test data, but providing a measurement uncertainty value with it. This is not the performance limits of a proficiency test, but it's the variance around the reference value that indicates its accuracy. So it has purposes beyond that of a QC for example, calibration of a method. Where does the uncertainty U derive from? We provide an expanded uncertainty, which is the sum of a number of different sources of uncertainty. The components combine the uncertainty of homogeneity, the uncertainty of stability, and the uncertainty of the reference value. This is a considerable piece of statistical work to do. It's an expanded uncertainty, which means that we provide a coverage factor based on 95% confidence limits. For simplicity, the coverage factor equals 2, so the expanded uncertainty is the uncertainty multiplied by that coverage factor. This is standard practice across the majority of analytical chemistry. You can see in this example that the expanded uncertainty is 1.1 compared to the standard deviation for proficiency of 2.68. That means the uncertainty of the reference value is much closer and with a tighter boundary than the performance limits, which represent the required reproducibility of an analysis. They are different statistics. The uncertainty gives you an improved accuracy, traceability, it's more useful for calibration, it's a defined confidence limit, and we also provide the datasheet with a confirmed stability. We provide that based on formal stability experiments, and it's not the same as a reproducibility performance limits. We provide reference materials. These are not certified reference materials, CRM. For all practical purposes, the Fapas reference materials adopt the same principles as if they were certified, but we do not have the certification process in place to call them certified. That is the only difference with our products. That's the end of this webinar on principles of proficiency testing for analysts, and it remains for me simply to thank my colleagues in Fapas and the customers without whom I wouldn't have any data to share with you, and thank you for your attention.
Cool.